Hello. So on my previous video, we're talking about this example on shunt faults. I basically showed you how to represent each shunt fault, each of the four, using the three symmetrical components and their expanded forms, how to compute for the fault current, for the fault currents on on line A, line B, and line C. Now, on that example, I used this system with a line connecting 1 and 2 and two machines that are both grounded. So now in this video I'll just emphasize the effect of the grounding or the ungrounding or of the grounded and the ungrounded machines into the network. So basically, I showed you the differences of the connections, how to connect your machines if they are ungrounded and your transformers if they are grounded. So to illustrate that, I'll modify the example that I'm using before. I still have the generator that's Y grounded. Now I'll be introducing a grounding impedance. Well, it's just the impedance of the grounding wire of the machine. And then I have a what do you call this? Transformer that is connected in Y grounded delta, and the fault still happens at bus 2 at the terminals, and the motor. Sorry, this should be a motor. The motor load is connected now instead of in Y grounded. It's now in Y ungrounded. So if we look at the expanded sequence networks, you still have the same sequence network for positive sequence. This is still 1 angle 0. I used the impedances of the line for the transformer impedance just to simplify the solution. Well, this is just for the purpose of comparison lang naman. For the negative sequence, it's still the same as before. However, for the zero sequence, so you'll notice the effect of the grounding impedance first. On this machine, take note, the zero sequence internal impedance is 0.05. However, you have to incorporate the grounding impedance. You have to multiply that by 3. So it's 3 times J0.1. So the idea is that for the zero sequence impedance, IA0, IB0, and IC0 are equal. They are equal in magnitude, equal in direction. Therefore, if those three zero sequence currents meet at the neutral, they won't cancel out. They are equal, so it's safe to say that IA0 is equal to IB0, which is also equal to IC0. So if they meet at the neutral, it's basically just thrice of IA0. So you have to incorporate that times 3 to 0.01. So that is why you have that times 3 there. That's the grounding impedance. Take note, that's not the grounding impedance of the fault, but it's the grounding impedance of the machine. On the transformer, it's in Y grounded delta, so it's in Y grounded. That is this connection here. This is your Y grounded connection here. It's connected basically, and then your delta shorts the transformer delta side to the neutral. So the fault is at bus 2, so that basically leaves you this open circuit between them. Okay, and then on the motor load, the motor load is ungrounded. It's Y ungrounded, so you leave an open circuit between the internal impedance and the neutral, and that's basically your zero sequence network for this system, with considerations on the grounding, on the grounded and the ungrounded machines. Okay, so you now have these three sequence networks. Then you just connect them in series or parallel, incorporate the fault impedances wherever necessary for different types of faults. So yeah, that is shunt faults.